Welcome back to Physics 30. This is the third part of the Friction Part 2 booklet. So we looked at objects being pulled or pushed on a horizontal surface, either at constant velocity or at an acceleration because there is a net force. So before we look at the last part of this, which deals with objects on a slanted surface, we'll look at a few other things. So summarize how the following can reduce friction. So a couple of things there. If you decrease the roughness of the surfaces, the smoother the surface, the less friction. So for example, Hot Wheels cars and tracks. Those smooth tracks and the wheels of the cars minimize friction, so like a Hot Wheels car can go for a long distance as opposed to being slid on the floor or on a wood surface. Anti-friction metals, so metals that are made up of different alloys of different elements can help reduce friction. Lubricants, a thin layer of lubricant between objects reduce friction. So greasing parts on a car, etc. That thin layer will reduce friction. Ball bearings will change things into rolling friction instead of sliding friction. So if you could cause objects to roll over top of each other as opposed to slide, that'll reduce friction as well. So kind of a summary of friction that we looked at. So at the start we talked about sliding friction, rolling friction, fluid friction, and here in Physics 30 we deal mostly with the ideas of sliding friction, whether it's static or starting friction. So static means at rest, beginning to get an object to move, or if the object is already moving, we're dealing with moving friction, or we refer to as kinetic friction. And of course the friction to start something is greater than the friction to keep it moving. Okay, so we'll look at the final few examples looking at objects that are on a slant. There's a specific geometry involved with that. So for example, a 57.3 kg trunk is resting on a plane at an incline of 30 degrees above the horizontal. Draw a free body diagram. So first of all, as this surface is being lifted up off the ground, the triangle of the surface and the triangle of this free body diagram are identical. So this 30-degree angle would be equivalent to this angle right here being 30 degrees. So the geometry is such that this is true. So this angle right in here. And some other things that we know, the force straight down is force of gravity. The normal force is no longer equal to the force of gravity. As we see, excuse me, the normal force is perpendicular to the surfaces. So it's equal and opposite to this, which I call F perpendicular, or the perpendicular force in this direction. And the force that the object experiences down the plane due to this surface being tilted is equivalent to this force right here, which I like to call F parallel. Parallel to the surface, perpendicular to the surface. So that is the key right there. So to figure out Fn, we need to know F perpendicular. To figure out the force applied down the plane, it's really F parallel. And of course Fg can be calculated by mg. So look at a couple of cases here. The first one involving no friction. So if there is no friction, no friction, so the force down the plane is all the force that we have. We don't have force of friction going in opposition. So to figure out the applied force down the plane due to that component of gravity, all I would need to do is figure out this. And so that's the opposite side of the triangle. If I could figure out the hypotenuse of the triangle, then I'd be able to use the sine law to figure that out. So the first thing to figure out is Fg. And we can look at it like this actually. Do it all in one step. Sine of theta equals F parallel over Fg. So I have it right there. And so to solve for F parallel, it's going to be sine of theta times Fg. So sine of 30 times Fg. Now since Fg is mass times gravity, mass times gravity. I guess I did figure it out separately here. I didn't do it all in one step. So over here, mass times gravity, 57.30 times negative 9.8. Fg is negative 561.54. Now, it really isn't beneficial to talk about negatives here, so we just simply use the force value. Because is this negative, this slanted angle? It's too hard to figure that out. Usually straight up is positive, straight down is negative. So we just forget about the negative for now. So sine of 30 times 561.54, we get 280.77. If I take it to 3 sig figs, 281. So the applied force down the plane, 281, and notice the direction here, it's not positive, not negative, just simply say down the plane. Acceleration of the trunk. So since there is no friction, my applied force is equivalent to F parallel here, as you can see. So F net is just simply equal to 281. So F net equals Fa, because force of friction is 0, so it's 281 newtons down the plane. So to figure out the acceleration, rearrange this equation. A is equal to F net over M, 280.77. Notice that I use the non-rounded off answer here, divided by mass, and I get 4.90 meters per second squared down the plane. Okay. Next, the normal force. So normal force, once again, equal and opposite to F perpendicular. So, and if I look at that, F perpendicular is the adjacent side over hypotenuse. So my FG is still the same as it was previously, 561.54 times the cos of 30, 486.3079 newtons, rounded off to 3 sig figs, 486. Now the direction here, I just simply called it angled up. So angled in this upward direction. Okay? So there you have it. So that is an example dealing with no friction involved. The next one we're going to be looking at will be involving friction. And the only difference here will be this step right here in figuring out F net. It'll be different than my F applied force or my parallel force. Okay, so if we look at that, well, I guess we have a few more things to calculate in this question here. Oh yeah, I see. So we just have this question continuing, except now, okay, what if the friction, there is friction and it's 0.30, the coefficient of friction. So we know the coefficient of kinetic friction is 0.3. Now we have a friction force. We have the normal force from previously, so we will be able to figure that out. And as you can see here, my net force will change here as well. So first of all, take a look here. To find the net force, we're gonna have to figure out the friction force first. The applied force is still the same thing. So Fk is equal to mu k times Fn. From previously, my normal force, as we saw here, 486, but I'll use the non-rounded off version, 46.3079, times my coefficient of friction, and I get 145.89237. My applied force, my parallel force down the plane, as we saw earlier, was 281, or 280.77 non-rounded off. So my applied force, took it to a few decimal places, plus my negative. Now remember, this is, even though I don't get a negative here, I insert a negative to get this formula to work. So F net 134.8776, or rounded off to be 135 newtons down the plane. The acceleration down the trunk now, it'll be different since that friction was involved. So it only works out to be F net 134.8776 divided by my mass, 2.35 meters per second squared down the plane. So you can see it's quite a bit less than the 4.90 that I had earlier when there was no friction. Okay, Over here, number 10, a 62 kilogram person on skis is going down a hill. It's sloped 37 degrees to the horizontal. The coefficient of friction between the skis is that. Draw the free body diagram, etc. So what I'm going to do is I'm going to stop the video now. See if you can figure this out, at least get the free body diagram and figure out a few of the answers. And then in the next part, part 4, we'll look at that answer and kind of summarize this all up. Okay, we'll see you soon.